Hi, I'm Errin Volitis, the research technician on the LoVoTECS project.
And I'm Ashley Hyde, graduate student at Plymouth State University. The purpose of today's video is to welcome new partners and provide background information on the network and to explain our use and focus on electrical conductivity.
LoVoTECS networks derives from the Lotic Volunteer Network, with sensors recording temperature, electrical conductivity, and stage or water height. This project is funded by the National Science Foundation's EPSCoR program. The network is coordinated by a group of researchers, staff, and students at Plymouth State University, and implemented by a broad group of partners including educators, researchers, government agencies, nonprofit organizations, and citizen scientists. Our goal is to improve our understanding of New Hampshire's water resources and help develop a technically advanced workforce by providing educational opportunities to interact with large data sets. To accomplish this, we have built a state-of-the-art, broad-scale, and high-frequency hydrologic sensing network using simple sensors. The sensors continuously collect data at an interval of 3 to 5 minutes during warmer months and 15 minutes during winter when access is difficult. The network has been designed to include all watershed sizes, shapes, and land uses. Here is a New Hampshire state map showing all of the LoVoTECS site locations. Most of the sensors were installed in 2012, while some were added in 2013. PSU plans to add regional sites in 2014. LoVoTECS volunteers play a fundamental role in maintaining and downloading the sensors. Without them, the network simply would not be possible. LoVoTECS has approximately 42 active volunteers that host sensors in 68 independent river or stream systems. Let's take a look at our local site and describe the equipment we use at each site.
We're here at Claybrook, one of our very first LoVoTECS sites, to show you an example of a sensor array. Each installation depends on the size and the substrate of the river, but here at Claybrook we've used a standard H-style installation. Both sensors are housed within the same protective PVC. The conductivity meter measures electrical current across two small plates on the sensor face. The water level logger measures water pressure using a pressure transducer. When paired with barometric pressure, we can calculate water depth. We have a handful of these same sensors that we use as barometric pressure reference sites. We capture data from all of these sensors using a waterproof shuttle, which stores the data on a memory card until we can connect it to the software to offload. Up next is Ashley with an explanation of electrical conductivity.
Electrical conductivity, or EC, is a measure of the ease with which electrical current can pass through water. For this network, we measure this in microsiemens per centimeter. Electrical conductivity increases with the number of ions in solution. EC varies with temperature, therefore we use an assumed relationship to adjust the measurements by 25 degrees Celsius. This gives us specific inductance. We can use specific inductance to estimate sodium and chloride levels in water, which gives us an idea of how NaCl, or road salt, moves through the watersheds. Road salt is an environmental concern because of its toxicity to aquatic organisms and its adverse effects on human health.
Today we will show you the specific conductance of 4 different solutions. We will measure it with a handheld EC Oakton meter, which our volunteers use in the field. The first sample on the right is deionized water. The second one in is water from the storm drain here in Plymouth. The third one in is from the stream Claybrook that we were just visiting. And the fourth one is an electrolyte drink. Because this is deionized water, we should get a reading of 0.0 microsiemens per centimeter. The sample is taken from the storm drain in Plymouth. We expect it to be much higher than the deionized water because of all the solutes that run off the road and into the storm drain. We'll give it a moment to equilibrate. So it seems to be stabilizing right around 3.96 millisiemens, 3,960 microsiemens. The sample is from the Claybrook site that we are just visiting. We expect this site to have a lower conductivity than the storm drain, but a higher conductivity than the deionized water. For forested sites, it's common to have lower conductivity measurements, and this site only has one road crossing, so there's not a lot of road saw applications nearby. Looks like we're stabilizing right around 22.6 microsiemens, which is pretty common for a forested site in New Hampshire. So this last sample is an electrolyte sports drink, which we expect it to be right around the same or a little bit lower than the storm drain measurements. They are a little bit lower. It's now reading 1.67 millisiemens, which is equivalent to 1,600 microsiemens.
Because EC depends on overall ionic concentration in water, it can be used as an index of total dissolved solids carried by a stream and therefore is indicative of water quality. The Class B New Hampshire Surface Water Quality Standard for chloride and corresponding specific conductance measurements are as follows. We can use specific conductance as tracer for rain events. Here is an example of a chemograph from Creamery Brook in Sandwich, New Hampshire. Prior to the storm start, we observe base flow conditions where conductance levels are stable. After rain enters the system, dilution occurs and specific conductance drops. In a forested site, it can take several days to recover to pre-event levels. At some sites, like the Pemigewasset River in Franklin, we see what's called a first flush. First flush is typically observed in urban catchments that produce a high pulse of highly concentrated runoff at the beginning of rain events. By studying the first flush, we can better understand contaminant transport within New Hampshire. This concludes our introduction to the LoVoTECS network. On behalf of Plymouth State University, we'd like to welcome you to the network and thank you for your interest in LoVoTECS. If you have any questions about electrical conductivity or our field and data procedures, please feel free to contact us.